All right, kiddos, I want to show you how to use proportions and energy conservation to talk about where in the cycle, where position-wise in the cycle, a simple harmonic oscillator will be at particular fractions of potential energy or kinetic energy or velocity. This is one of the things we should be able to do. So I just want to point out that when we are at an extreme end, whether that's the left end or the right end, all the energy is potential. All of it's potential. And when we are in the middle position, then all of the energy is kinetic, right? All of our energies turn to green, to kinetic energy in the simulation that happens. When x equals 0, the maximum position, we tend to call that the amplitude, because that's what the maximum displacement is going to be. Okay, so I'm going to flip over here to look at, to draw this out for you guys, a little bit of practice. We did this in class today. If you missed, then this is an opportunity for you to catch up. If you were with us but you struggled a little bit with it, then this is an opportunity to try again. So I just wanted to summarize that since we know that when x is equal to a, then we have a maximum potential energy, and that is all of our energy, right? The total energy is going to be equal to these two combined, the mechanical energy will. And when we're at the midpoint, then our maximum kinetic energy is going to be based on our maximum velocity instead of based on the maximum position. So we're going to refer to that in a little bit. Let's do, let's say the question that we're supposed to ask is at what point in the cycle, at what x value in terms of A will we're going to have, the first thing we're going to do is, will the potential energy be equal to a quarter of the max? Okay, so in order to do this, I actually don't need my chart. All I need to know is that potential energy is equal to 1/2 of k times x squared. Why am I starting with that? Because my goal is to find position. So right here, I've got my position for the point that I'm talking about. And that's going to be equal to a quarter of what? Of the maximum potential energy, which is going to be based on 1/2 of Ka squared. So I'm going to put 1/2 Ka squared. Okay? And so that's what we're going to work with right here. I forgot to have the 1/2. My bad. That's okay. I can squeeze it in there. It's a quarter of the maximum potential energy, which is 1/2 Kx squared. So what we are going to do now is just solve for x. So I can multiply by 2, or I can recognize that there's a 1/2 here and 1 here, and they'll cancel. I could divide by x, or I can recognize that they'll cancel. And so that leaves me with my new x squared, is what's left here, will be equal to 1/4 of the amplitude squared. And if I take the square root of each side, then that means that my new x will be equal to the square root of 1/4 times a squared, and that simplifies to 1/2 of a. So we could flip back over that simulation. You're welcome to do that. It's at ophysics.com. You're going to go to the wave section, and I think it's the second item in the wave section. But this tells me that in that cycle, if we're moving back and forth between the amplitude and a 0 and another amplitude, that would be positive and negative, we're going to have at the midway point between there, when x is equal to a over 2, that's when I expect to have a quarter of the potential energy. Okay, cool. What if we ask a new question? What if instead of being told we're going to have a quarter of the maximum energy, what if we said our kinetic energy will be a quarter of the maximum? When you do your math in the project that I've asked you to do this year, then I'm going to expect for you to use a different fraction than 1/4. You at least have to do that, okay? We really want to get to where you understand this. So if we tried the same thing and we started out by saying, well, I'm going to put 1/2 of mv squared, it's going to equal 1/2 of m times v max squared times a quarter, then what that would help me do is define what my V value is. But that's not what I'm trying to find. I'm trying to find what the X value is. So this technique's not going to help me progress towards the answer. What I actually would like to do is find out, well, if I have a quarter of my energy is kinetic, then how much of it is potential, so that I can go and kind of do the same thing here. If I can find what ratio I have of kinetic and so let's go over here and take a look at our bar chart and say, well, if at our new position here, if I have a kinetic energy that's 1/4 the amount, then how much potential energy should I have? And because I know that the total should still be the same, that means that I should have whatever's left over here, I should have 3/4. That's probably not 3/4, but you know what I'm saying. If I have 1/4 of my energy is kinetic, then because the maximum kinetic energy is this amount, if I have 1/4 of that here, I must have 3/4 of my energy is potential. And so then I can use that over here, and I can say that that means that I'm going to have 3/4 of my energy is the potential energy. My potential energy, I guess, is 3/4 of the max. Maybe that would be better if I wrote it like that. Come with me, and you'll see a world of pure imagination. That leads me to know that my new energy is equal to 3/4 of that. Okay, cool. So then we're just going to do what we did before. We said U is equal to quarter max now. Now we're going to use U is equal to 3/4 max. And last time I said, well, let me talk about my new X. So my new X is going to be based on 1/2 of kx squared. And so that's going to equal 3/4 of 1/2. What was the maximum potential was 1/2 of Ka squared. And now I'm just going to cancel out the 1/2 of K like I did before. And that tells me that my new X is going to be equal to the square root of 3/4 of A squared. Or in other words, square root of 3 over square root of 4, which is 2 times A. So that's going to be my answer right there. See, that's something people would not normally guess on a multiple choice test. So it's important that you can go through the steps to support it, because you're not going to intuitively think, oh, that feels like the right answer. You can't skip the steps in the middle. The third option for this is the most complex, but hopefully we're seeing the patterns, right? Because in order to talk about at what position we're going to be at, we need to find out how much potential energy we have. When we didn't know how much potential energy we had, we needed to use conservation of energy to figure out how much potential we would have, and then we could work it. Well, now our new scenario, what we're going to say is that our new velocity is going to be 1/4 of the maximum velocity. And if that's the case, what's that tell us? Well, the first thing I'm going to do is say, in order to find out about this position, because it's a conservation situation, I better go and find out about the potential energy. And in order to know that, I need to know about the kinetic energy. So we're going to say that my new kinetic energy is going to be equal to, well, I guess let me just define it like the way that we've done it a bunch of times. We first would define the value that we knew about, right? And then when we did a factor of change method, we said if I have a new kinetic energy value, I'm going to look at the separate factors compared to the old one. So each of these things could be multiplied by something, but in our new kinetic energy, it's still going to be 1/2 of m. So those things have a factor of 1 because they're not changing. The only thing changing is the velocity. That is now 1/4 of what the maximum velocity was. So, and that is squared in my equation. So I'm going to square it here. And that tells me that I have 1/16 of the maximum kinetic energy with my new value. So if we were going to come over here, we're going to change this up. This isn't 1/4 anymore. This is now 1/16. And that means that this must have grown to be 15/16. So that together they add up to 16/16, a whole value right there. So now what I'm going to do is just finish the rest of this. If that's how much maximum kinetic energy I have, my kinetic energy is a 1/16 of the max, that means that my U value is going to be equal to 15/16 of the max. And if that's the case, now we're back to what we did on the first question. 1/2 of k nu squared is going to be equal to 15/16 of the maximum kinetic energy or potential, which is found by 1/2 of Ka squared. And we're going to cancel out the things that are the same, and then my new value is going to be equal to the square root of 15/16 of a squared, or in other words, square root of 15 divided by square root of 16, which is 4, times square root of a squared, which is a. So this is where it's going to be. It's going to be square root of 15 times 4, or you could do square root of 15, basically almost all the way, right? When we end up with 1/4 of the speed, we're going to end up being almost all the way to the amplitude. Okay, cool. All right, well, hopefully that helps you to get a plan for how to use energy and proportions to find positions. Positions are always going to be connected to our potential energy. So if they give us kinetic energy makings, then we need to get to potential energy. And the fastest, easiest way to do that is going to be through this. Make sure that you are using a different fraction to try this out on your own. And come check with me if you need some help. Best of luck.